are doing the topic DC circuits or current electricity, you will certainly come across the problems on the cubes, that is cube skeletal, where all the edges they have a resistance R. So this is a cube skeletal made of resistances. Each edge has a resistance capital R. So we have 12 edges, that's why we have 12 resistances connected this way. And we are asked to find the equivalent resistance between the various points. So we may be asked to find the equivalent resistance between two vertices on the same edge, like between A and D. What is the equivalent resistance? If we talk about between A and D, the same will be between A and E, A and B, B and C, because all of them they are the sides. Or we may be asked to find the equivalent resistance between the diagonal of a face. If this is A, B, C, D makes a front face and E, F, G, H that makes a back face, so the diagonal of front face is AC. So what is the equivalent resistance between the points A and C, or B and D, or H and F, or E and G? That will obviously, one we find out, it will be same. So whatsoever be the equivalent resistance between D and B, same will be between H and F, or G and E, or C and A, because that is one and the same thing because of symmetry. Or we may be asked to find the equivalent resistance between the longest diagonal of this cube, like A and G, this is the longest diagonal in the cube, or E and C, or F and D, or B and H. So these are the longest diagonals. So one is, we may be asked to find the equivalent resistance between the two vertices on the same edge, diagonal of one face, or the longest diagonal of the cube. Earlier in this course we had solved it using Kirchhoff laws. Now let's find the equivalent resistances using the method of symmetry and joining the points which are on the same potential. So let's first of all we find the equivalent resistance between the longest diagonal. Let's say this is D and F. This is the longest diagonal, that makes D is on the front face A, B, C, D, and this is lower left, and G, H, E, F, that is a back face, and that is top right. So this is D and F, that makes the longest diagonal. So D and F, that makes the longest diagonal. And we have to find what is the equivalent resistance between D and F. So for that, what we do is, we assume, let's say the current is entering from here, I current is entering from here, and I current will obviously exit from here. We can imagine, we can assume that it is connected by a battery, this being a positive terminal, and the current is flowing like this. Whatsoever the current will enter into this network, obviously the same current will exit from here, because we have to find the equivalent resistance between D and F. Had it been between D and C, then we would say current enters from here and exits from here. But right now we are interested in finding the equivalent resistance between D and E. So current enters from here and exits from here. Now the first thing to see is, that is, when the current is over here, it can go three ways. One is this path, the other is this path, the third is this path. Whenever we have option, whenever the current has options over here, we'll look out whether these three paths they are identical or not, whether they are symmetrical or not, whether the same current will flow through all these three paths or not. To know whether the same current will flow into this resistance, or into this resistance, what we look out for? We look out for the shortest path between the entry point and the exit point. Number one, this is the shortest path we are looking for. Once we have identified the shortest path, then we look out for the resistances, whether the current will come across the same kind of a resistance or a different kind of a resistance. If the shortest path is same for all the options and the resistance offered during this path is also same, then the same amount of current will flow across this, and across this. So if this way it enters, the shortest path is one resistance, second resistance, third resistance, and it exits. So this seems to be the shortest path, but let's look out for the other path. So the other could be 1, 2, 3, exit. So once the current enters over here, the shortest path constitutes at least of the three resistances. If the current enters over here, so it is 1, 2, 3, exit, or 1, 2, 3, exit. The shortest path still constitutes of the three resistances. If we talk with a longer path, it could be anything. We can say current goes over here 1, 2, 3, 4, 5. It could be anything. But we are bothered about the shortest path. So for the current, if it enters over here, it has 1, 2, 3. That is, this is the shortest path. For this, 1, 2, 3 exit. For this also 1, 2, 3 exit. So whether the current enters over here or current enters over here or current enters over here, it will have to come across the three resistances, and all the three resistances, they are of the same value. All the resistance, they are equal to R. Had it not been R, then certainly the current would be different, which shall be flowing across this and across this resistor. But right now all the resistance, they are equal to R, so it means the current will divide equally. It doesn't have any reason to prefer one path over the other. So I by 3 will flow this way, I by 3 will flow this way, I by 3 will flow this way. We are just bothered about, that is, whether these currents are same or not. We are not going to use KCL or KVL. We are going to identify the points which are the same potential, and from there we shall proceed to find the equivalent resistance. So over here, if we see, that is one point, that D is obviously going to be at one potential. So resistance is this resistance, this resistance, this resistance, all the resistances they are same. So it means if the current is also same, resistance is also same, the potential drop will also be same. So whatsoever the drop across this resistor, the same potential drop will be across this resistor, the same potential drop will be across this resistor. It means C, H and A, these are the points which are going to be at same potential. I remove this circle, so that circle signifies that these 3 points, they are the same potential. If we are looking from this side, so these 3 points, they are same potential. If we look from this side, G, B, and from here to here, E, that is going to be same potential. From here, C, H and A, they are at same potential. If you look from here, because of symmetry, G, B and E, they are same potential. Please understand the potential of this and this is going to be different. A, H and C, because the current is flowing from here to here, in this direction it's flowing, so C, H and A, they are going to be at higher potential, and these points E, B and G, they are going to be at lower potential. It may happen that is all of them, they are at 10 volt potential, and all these they are 7 volt potential. Their potential is same, their potential is same, but that doesn't mean the potential of this and this is same. There is potential difference. So now what we see is, that is these 3 points, they are the same potential, and this G, B and E, they are same potential. It means even if we connect them by a wire, conducting wire of zero resistance, there will not be any flow of current, because for the flow of electric current, there has to be a electric potential difference. There is no potential difference between this and this, between this and this, and similarly there is no potential difference between C and H, between H and A. So it means even if we connect them by a wire, there will not be any flow of current. Or collapse it, A, H and C, we collapse it, is primarily a skeleton only, and this is of wires. So wires, they are flexible. We can just compress and we can join A, H and C. Similarly we can join G, B and E. So our network, it takes a shape like, if we have over here, so we have D junction over here, C, H and A, they have been, C, H and A, they have been compressed, they have been combined together. So the resistances between this, they will also be connected from here to here. D and C, let's connect between D and C. D is here, C junction is here. Between D and C we have a resistance, so this resistance is over here. We also see that there is a resistance between D point and H point. Between D and H, D is here, H is here. This has also been considered, so that's why I put a cross. Between D and A, let's consider now, D is here, A is here, considered. So we have done away with the 3 resistances, done away. Now let's go to F. So F junction is here. Now when we are going to join E, B and C by a wire, or we directly press it against each other, so B, E and G will be here, junctions will get connected over here. Between F and E, these are joined by resistance. Between F and G, they are joined by resistance. I put a cross. F and B connected. F is here, B is here, connected. F and G, they are also connected. F is here, G is here, connected. Okay. So how many wires do we see over here? 1, 2, 3, 4, 5, 6. Total number of edges in the cube, that is 12. So we have 6 more wires to get connected. Over here we see A and E. A is here, E is here, A and E connected. A and B, A is here, B is here, connected. So the top face is done, we have put all the crosses. Now let's look at the vertical edges. This is done, B and C. B is where? B is here, C is here, B and C. E and H, H is here, E is here. So all the vertical sides they have been done with. Now over here, H and G, H is here, G is here. Then G and C, G is here, C is here. So now what we see is these three resistances, each of are in parallel between this and this. So this is R by 3, our point of interest D is here, and on this side we have F, across which we have to find the equivalent resistance. 1, 2, 3, 4, 5, 6. So this is each resistance equal to R, and all the resistance they are in parallel. So 1 by R plus 1 by R plus 1 by R plus 1 by R and so on 6 times. That makes the equivalent resistance as R by 6. And from here to here, once again R, they are parallel. So that makes R by 3, and over here we have F. So R dash comes out to be 5 by 6 R. So this is the equivalent resistance between D and F, that is across the vertices of the longest diagonal in the cube.